Previous lecture, we have solved few numericals based on the various types of charge distributions, and we have studied case study, that is analogy of parallel plate capacitor, and we have studied streamlines. Okay, we'll continue with the streamlines and sketches of fields of the previous chapter, and we will continue with the next unit, that is unit 2, chapter 3, that is electric flux density, Gauss law and divergence. Just I will brief out what we are going to study in this chapter later. First, we'll study the streamlines and sketches of fields. Already in the previous class, I have told picture speaks louder than words. Instead of telling something, some scenario in 1,000 words, it is better to draw just a perfect diagram or clear diagram so that the people will understand, right? Okay, what are streamlines? Already I told in the previous class. Uh, we know that the electric field lines, we call it as lines of force around a charge. If I have the charge, the lines of force are around the charge. We can call them as lines of force or electric field lines or simply field lines, direction lines, flux lines, streamlines. All are one and the same. Please keep in the mind, right? All are one and the same, right? Okay. Then I have a infinite line charge. Let me assume that I have a infinite line charge having line charge density rho L. Then I want to represent its a field. Then what I will do? Yes, everywhere the field will live normally to the cylindrical surface. Just what I can show here, right? Okay, this is the best way what I can draw. Suppose let me assume this is positively charged, right? This is what I can show you people. But observe from top. So everywhere the field lines are living normal to the cylindrical surface. Observe from the top. Just I can represent as shown in the 4 figures here. The field due to infinite line charge or streamlines of the infinite line charge are shown in 4 figures. Which is better, I will tell you. Figure A I can represent like this or like this. Figure C and figure D. Which is better, I will tell you. You can observe here. I am looking from the top. Yes, the point charge is here. Sorry, line charge is here. Then the field lines. You can see one line is shorter, one line is bigger, right? So this is a very poor sketch. I hope this is fine, but this is a very poor sketch. So I will not prefer this. Poor sketch of a field. We call it a streamline, right? Poor sketch. So I will not prefer this. So next, we'll consider the figure B. Yes, line charge is shown as a dot here, right? Because we are looking from the top. If I look from the top, it appears as a point charge. Sorry, just like a dot, right? Yes, this is also fine. As compared to figure A, figure B is better. But if I look at point A here and look at another point B away from this line charge, the field intensity should goes on increasing. But looking at this diagram, we will come to know that the field intensity is almost same because we are drawing the same lines with same intensity and same thickness, right? But coming to the figure C, okay, you can observe here. If I look at point A here somewhere, and if I look at point B here, right, you can observe here. Here they have taken the lines are very thicker. The next, the field lines which are moving away from the infinite line charge, still, right, the thickness has been reduced. The thickness goes on reducing. This is better sketch as compared to figure B because this indicates that the field intensity goes on decreasing as I move away from the infinite line charge. The intensity goes on decreasing. So this is the good sketch or better sketch for the streamline of a infinite line charge. But I cannot keep on drawing the, yes, this is thick, still lighter, thin and thin, so on. I cannot do that. So what I will do, so I will go for practical approaches. I will go for this. Practically, I will go for this sketch. This is preferred. Practically, I will go for this sketch of the streamlines of the infinite line charge, sketch of the field of the infinite line charge. So this is preferred, right? Practically. So this is fine. This is accurately fine. Figure C is good, but practically this is not feasible. I cannot waste time in drawing the field lines. So I will go for figure D in order to represent the field of the infinite line charge or streamlines of infinite line charge. I hope you understood. We will wind up this chapter here and we will continue the next chapter, that is unit 3, chapter 3, that is electric flux density, Gauss law and divergence. In this chapter what we are going to study, I will brief you out. Electric flux density. In the previous chapter we have seen the electric field intensity, right? Force acting on the unit positive test charge. Here we will introduce one of the new parameters, that is electric flux density, means the number of electric flux lines or lines of force leaving the particular surface area. So that is electric flux density we will study later. So with respect to that few parameters, Faraday's law also we are going to study, that we'll see. Then next, apart from Faraday's law, we are going to study the Gauss law. Faraday's law means Faraday's experiment actually. We'll see that. Then Gauss law we'll study, and we'll see the applications of Gauss law. Means in the previous chapter there were four types of charge distributions: point charge, line charge, surface charge, and volume charge. And we have derived the electric field intensity due to all these four types of charges. But by making use of Gauss law, once again we will try to derive the electric field intensity, or in turn the electric flux density due to point charge, line charge, surface charge, and volume charge. So how it is different from we have made use of Coulomb's law there. So we will make use of Coulomb's law, Gauss law, and we will try to derive all these electric flux density for point charge, line charge, surface charge, volume charge. We will see that. That is applications of Gauss law. Then divergence and divergence theorem. Yes, everywhere field, if I take point charge, a line charge, a surface charge, volume charge, the field is moving away from the charge, right? If it is positive charge, the field will repel, it moves away from the source. But if it is negative charge, the field lines will approach the charge, particular charge, if it is positive charge or negative, based on that, right? So divergence, this is the quantity. What is divergence we'll study, means this, we will use this mathematical concept, that is divergence and the divergence theorem, to study the spreading nature of the field. Yes, the field is spreading in the space, right? In order to study that spreading nature of the field, we take the help of the divergence and the divergence theorem. Okay, all these things we are going to study in this chapter. That is unit 3, chapter 3. Is it fine? Electric flux density, Gauss law, and divergence. Then okay, flux lines. Yes, we are already familiar with what is this flux lines, but the new term has been introduced. But we are already familiar with, yes, field lines. We know what are field lines. The lines of force around a charge are nothing but the field lines, right? Also we call it as streamlines or direction lines. And one more term, we can also call these lines of force around a charge as flux lines, right? We are introducing the new terminology for the lines of force around a charge, that is flux lines, right? I hope you understood this. Next, Faraday's experiment. Yes, what Faraday has done and what conclusion he has made, we'll see here. He has conducted one experiment. Okay, he has taken two concentric metallic spheres, right? Concentric metallic sphere means one sphere within another sphere. Okay, he has taken one smaller sphere, right? And it is positively charged, plus q, right? And he has taken another bigger sphere, which he encloses the smaller sphere within the bigger sphere, right? He has taken this bigger sphere, the smaller sphere is enclosed within the bigger sphere. Okay, these are two metallic spheres, right? This is also metallic spheres, right? This is a metallic sphere, and the inner one, this is a metallic sphere, right? And in between the two metallic spheres, there is a dielectric material or media, dielectric material. He has inserted some insulating material in between the two concentric metal spheres, dielectric media, right? Or material, we call it as media or material, no, one and the same, right? So what he has observed, and the outer sphere, initially what he has done, he has grounded so that all the charges are removed. He has grounded initially. Then what he has observed is, right, the charge induced on the outer sphere is exactly opposite, that is minus q. Means there is, right, this is a positive charge, means the field lines are living in this direction everywhere, right? This is sphere, right? The field lines are living everywhere here. Then this we call it as flux lines or lines of force or field lines or streamlines, one and the same. But we call it as flux lines, right? Okay, the inner sphere is charged plus q, and it induces the same the magnitude of the charge is same but opposite in sign, means it induces the negative charge on the outer sphere. So this is what he has observed, right? So this is the Faraday's experiment. So for flux lines, we will use the notation symbol psi in order to represent the flux lines or electric flux lines. Instead of simply saying flux lines, I can say electric flux lines. Instead of saying simply field lines, I will say electric field lines, right? Flux lines, electric flux lines, all one and the same. So in order to represent the flux lines, we will say psi. Psi, they represent the flux lines, and it is equal to, or it is proportional to, the amount of charge enclosed, means the amount of flux lines leaving the inner sphere, they are living in all the directions, is directly proportional to the total amount of charge enclosed, right? So those are the flux. I want to study how many number of flux lines are leaving this outer sphere. right? So it is directly proportional to q. But luckily the proportionality constant is 1 here, and it is equal to q because we have chosen the SI units, right? SI in SI units the proportionality constant is 1. So what we can say, psi equal to q means the number of electric flux lines. These are the flux lines, right? The number of electric flux lines leaving the outer sphere is equal to the total amount of charge enclosed by the outer sphere. Psi equal to q. He has told this, and the unit of q, that is charge, is coulombs, right? Coulombs. Similarly, the unit of flux lines or flux is coulombs, same as charge, right? Simply instead of writing coulombs, we will write C, coulombs, right? And another name for this flux lines, we call it as displacement flux or electric flux, one and the same, and it is represented by psi, the symbol already I told, with the Greek letter psi, right? So why we call this as displacement flux means the flux lines are displaced from the inner sphere to the outer sphere, right? The flux lines are living from inner sphere to the, they are displaced, they are moving. Hence, we can call these flux lines as displacement flux. Another name for flux lines is displacement flux, or simply we can call it as electric flux psi, right? One and the same. Then next, we'll try to understand what is electric flux density. Already we have studied the electric field intensity. The electric field intensity E vector is equal to the force experienced by the unit positive test charge, FT. The force experienced by the unit positive test charge, right? This we have defined, right? There we will place the unit positive test charge in the field of either point charge or line charge in some source, and what is the force experienced by the test charge, we call it as electric field intensity. Then we will differentiate between electric flux density. We will take the help of the letter D vector, right? So we will define the electric flux density is the flux passing through the given surface area. Means the flux means the flux line psi, flux passing through the given surface area, right? So here in the previous this is the surface area, the outer sphere. This is the surface area. Surface area of a sphere is 4 pi r square. If radius is r, 4 pi r square surface. The total amount of flux lines leaving this surface, that is psi. So flux passing through unit surface area, flux passing through the given surface area, we call it as electric flux density. So psi, it is equal to q, right? So coulomb per meter square. Surface area is measured in meter square. Coulomb per meter square, and here practical units is volt per meter. So we have differentiated between electric field intensity and electric flux density. The number of flux lines leaving the closed surface area or given surface area, we call it as the electric flux density. And electric field intensity is force experienced by the unit positive test charge in the field, right? Okay. Simply I have written here electric flux passing through the given surface area, and this is the formula, right? This is written in bold letter, right? If we write, we have to write it like this: D vector. Since it is bold, it is a vector. D vector is equal to flux passing through unit surface area, and unit is coulomb per meter square. Okay. In the previous slide, we have taken just two concentric spheres, but let me assume that the inner sphere, these are two metallic spheres. The inner sphere is having radius A, and outer sphere is having radius B, right? Then we will make use of the definition of electric flux density, and we will try to calculate what is the electric flux density at on the inner sphere and what is the electric flux density on the outer sphere, right? So on the inner sphere radius r is A. So the electric flux density on the inner sphere is given by the flux passing through unit. So we will make use of this definition, psi by s. Psi, what is psi? Psi is equal to q. So psi is equal to q. The total amount of charge present on this surface area is q. Q by 4, surface area of a sphere is 4 pi r square. What is the radius of inner sphere? It is A. So 4 pi a square. Then what is the direction? The direction of the field line. So it is in radial direction, right? In radial direction everywhere. So AR. So the electric flux density on the inner sphere is given by Q by 4 pi a square into AR. Similarly on the outer sphere, S flux psi is equal to Q, and surface area of the outer sphere radius is B, 4 pi r square, that is B square into AR. So this is the electric flux density, the number of flux lines crossing this outer sphere, the number of flux lines crossing this inner sphere, right? We have given the formula. Suppose the let me take one of the metallic sphere here in between. Here it is not shown, just I will draw it. You can observe here. Let me take here. Let me call this radius as r from here, r, and here r lies between A and B. You can see here, right? we'll choose one of the metallic sphere in between the inner metallic sphere and outer metallic sphere. We'll choose in between some surface, closed surface, which is spherical surface, right? So the radius is r and it lies between A and B. Then I want to find out what is electric flux density leaving this closed surface. So it is nothing but Q, the total amount of charge enclosed by this is Q only, Q by 4 pi r square into AR. This is the general formula, right? I hope you understood this. The electric flux density on the inner sphere, outer sphere, and the electric flux density between the inner sphere and outer sphere, Q by 4 pi r square into AR. I hope you understood this. If any doubts, you can unmute yourself and you can ask instantly so that I can clarify your doubts. Okay, next we will make use of the concept of electric flux density and we will try to calculate what is the electric flux density D due to point charge, right? So we know that the electric flux density is flux passing through unit surface area, right? So if it is smaller surface, the small amount of flux lines leaving the small amount of surface area dq by, so I will not take the vector, just I will take the magnitude, flux passing through unit surface area. If it is the total surface area, I can write it as the flux passing through unit surface area, one and the same, right? So if it is smaller surface, I will consider small amount of flux lines, d psi I can represent. If I consider the entire surface, the total amount of flux lines leaving the given closed surface is flux passing through psi by s, one and the same, right? For this is for smaller surface, this is for the entire surface, right? So we will try to find out what is the electric flux density d due to point charge q. And we have already seen what is electric field intensity due to point charge E in the previous chapter. And the formula what we found out is Q by 4 pi epsilon naught R square into AR. This is the formula what we got, right? This is the electric field intensity E due to point charge, volt per meter, right? Next we will try to derive what is electric flux density D due to point charge Q, right? So I will take point charge here plus Q at the center of the spherical coordinate system S, and I will consider the closed surface. This is the plus Q, point charge is located here. So I will consider the closed surface. It can be any shape, but here I am considering the sphere, but I am drawing it as a circle here. Actually it is a sphere, right? Yes, imaginary spherical surface, imaginary spherical surface. It is closed surface. Yes, it is closed one because it is enclosing this point charge. So it is the closed surface. No need to say imaginary spherical closed surface, imaginary spherical surface. It is a closed surface. And this imaginary spherical surface, we call it as Gaussian surface also. I will tell you why later on. Right now, I will introduce the term Gaussian surface. Gaussian surface. Simply I will write GS. GS means Gaussian surface. So Gaussian surface or imaginary spherical surface. And the radius of this imaginary spherical surface we will consider it as R, right? And everywhere the field lines are living in radial direction. So I will call the unit vector is AR, right? Okay, I will make use of the definition of electric flux density, right? So here we have seen flux passing through unit surface area. So D is equal to flux passing through unit surface area, right? Then I will make use of this. So psi, what is psi? By Faraday's law, we have seen that the total amount of charge enclosed by this imaginary spherical surface psi is equal to Q, right? Then what is surface area of the spherical surface? So surface area is 4 pi r square, surface area of a sphere, r square. What is r here? It is r only, 4 pi r square, right? So I'll substitute psi and s here. So D is equal to Q by 4 pi r square. Then I want to associate the vector. So D vector is equal to, it is the field everywhere is in the radial direction. The flux lines are living everywhere in the radial direction of the sphere. So AR, right? I hope you understood. This is the electric flux density due to point charge. And if what is the unit? Q, that is coulomb per meter square. Coulomb per meter square. You can observe the electric field intensity due to point charge is Q by 4 pi epsilon r square into AR volt per meter. and the electric flux density due to point charge is q by 4 pi r square into r. You observe both the differences, right? So instead of this capital R, what I will write? I will rewrite the electric field intensity equation q by 4 pi epsilon naught q by 4 pi epsilon naught r square into ar. If I locate the point charge at the center of the spherical coordinate system, just observe this equation and observe this equation. So what is the relationship between D and D? What is the relationship between electric flux density and electric field? Can I write like this? D equal to epsilon naught E. Can I write? Just observe here. This is the relationship between D and D. So D I have here, and if I multiply epsilon naught for E I have, just multiply epsilon naught, epsilon naught will get cancelled. I am getting D only, right? Q by 4 pi r square into R. So the relationship between D and E. For point charge, we will in the same case for line charge, surface charge, sheet charge, volume charge, we will see. What is D due to point charge? Yes, D due to point charge, already we have seen. D due to point charge is q by 4 pi r square into r. We have proved this. Q by 4 pi r square into ar, right? And E due to point charge is q by 4 pi epsilon naught r square into r. We are familiar with this. This is due to point charge. Next we will see the line charge. So E due to line charge we know. So it is rho L by 2 pi epsilon naught rho into a rho. This we know, right? So this is line charge, infinite line charge. Then we know the relationship between D and D. D equal to epsilon naught E. Just multiply epsilon naught for this. Epsilon naught will get cancelled. So D due to infinite line charge is rho L by 2 pi epsilon naught will get cancelled. Rho into a rho. This is the formula for electric flux density due to line charge. Then sheet charge we will take. Sheet charge. For sheet charge, rho s by 2 epsilon naught into an, the unit normal vector. This is for sheet charge. Then we know the relationship between D and D. It is just multiply epsilon naught for this. Then the electric flux density due to sheet charge, infinite sheet charge, is given by rho s by 2. Epsilon naught will get cancelled. Rho s by 2 into the unit normal vector. I hope you have understood. This is electric flux density due to point charge, due to line charge, due to sheet charge. Then I am left out with volume charge. We will see what is electric field intensity E due to volume charge. So this we have seen, volume integral of Q. Q is nothing but volume charge density rho V into dV divided by 4 pi epsilon naught r square into R, right? R square into R. So this is for volume charge. Right. Next, I want the electric flux density D due to volume charge. So I will write the formula. Just D equal to epsilon. We know this. So volume integral of rho V into dV divided by 4 pi epsilon naught will get cancelled. 4 pi r square into R vector. So this is due to volume charge. So we have seen the electric flux density D due to point charge, line charge, sheet charge, and volume charge. Right? We know the electric field intensity due to point line we have written, and we know the relationship between D and D. Using that relation, we have seen what is electric flux density due to point, line, sheet, and volume charges. Right? But we have derived what is electric flux density D due to point charge here. We have derived it, right? So and it is D equal to Q by 4 pi r square into AR. Right? I hope you understood the relationship between the electric flux density and the electric field intensity. Right? Next we will solve, I hope we have studied the electric flux density. Then next we will solve few numericals based on that electric flux density. If any doubts, you can unmute yourself and speak to me so that I can clarify your doubts as and when it comes to you. Okay. Find, we don't want this. Find the electric flux density D vector in the region about a uniform line charge of 8 nanocoulomb per meter lying along the z-axis in free space. Then assume the radial distance rho equal to 3 meters. Find the total flux leaving a 5 meter length of the line charge. Okay, we'll try to do this. V due to infinite line charge we know. Similarly, we know D due to infinite line charge. Right? So Okay, let me write the draw the diagram, because uniform line charge 8 nano, it is lying along z axis in free space, right? So let me draw the diagram. X axis, y axis and z axis. So it is lying along z axis, entire z axis, and this is the line charge rho L, and it is equal to 8 nano coulomb per meter. It is in free space, right? Free space. Why they are giving free space means epsilon r is 1, so epsilon is equal to epsilon naught, and epsilon r is 1, relative permittivity, and right, that is the meaning, right? Okay, then find d in a region about a uniform line charge. In means surrounding this, let me consider one point here. What is d at this? This is the source point and field point somewhere here. So what is the electric flux density at this point, right? So electric field intensity we have studied already. So next, the d due to the infinite line charge is given by rho L by 2 pi. Don't write epsilon naught, because epsilon naught will cancel. We have the formula here. 2 pi rho into a rho. This one we have to use, right? Right, epsilon naught should not come into picture, because d equal to epsilon. If you are having confusion, write down e, then multiply epsilon naught and write down this. Rho L by 2 pi rho into a rho. Into a rho. Right, this is the formula what we are going to use. So rho L is how much? 8 nano divided by 2 into pi into radius. Assume rho equal to 3 meters I have given. So it is 3 into a rho, radial direction. So calculate this. So 8 exponential minus 9 divided by 2 into pi into 3. So it turns out to be 0.424. What is given, I will write the same thing. 0.424 into 10 power minus 9 into 10 power minus 9 a rho. And d vector finally I will write 0.424 nano coulomb per meter square, right? So let me write nano, let me take it outside. So a rho 0.424 a rho nano coulomb per meter square. Sorry, nano coulomb per meter here, right? Is it fine? Sorry, it should be not coulomb per meter, because the flux density is coulomb per meter square only. See here. Here rho L is coulomb per meter and this is meter, coulomb per meter square, right? So here they have given wrong. This is wrong. Coulomb per nano coulomb per meter square. 0.424 a rho, nano means 10 power minus 9 nano coulomb per meter square. This is correct. This is wrong, right? Next, find the total flux leaving a 5 meter length of the line charge. Yes, this is infinite line charge. We have considered this as infinite line charge, but let me restrict. This length is 5 meters. Let me take only from here to here, it is 5 meters. Then what is the total amount of flux leaving a 5 meter length of the line charge, right? So we will enclose this in the closed surface. We will try to enclose this in the closed surface, right? We have enclosed it, but the better suitable enclosure is actually the cylindrical surface. Suppose I have the infinite line charge, the closed surface that would be better is the cylindrical surface would be better. This is the closed surface, Gaussian surface or imaginary surface, right? So this is 5 meters. Then find the total flux leaving a 5 meter length of the line charge. Means total flux psi. What is psi? Well, they have asked, right? And rho L is how much? 8 nano coulomb per meter. 8 nano coulomb per meter. Then I want to find out Q. What is Q? It is nothing but psi only, right? So what is rho L? Charge per unit length, right? Charge per unit length. So what is Q? Q is equal to rho L into L. So what is rho L? 8 nano, 8 into 10 power minus 9 into L. L is length of the line charge. It is 5 meters, right? So Q is equal to 8 5 40 nano coulombs. So psi equal to Q, and that is equal to 40 nano coulombs. So it is not a rough work. Actually, the main calculation should come here, right? So The total amount of flux leaving a 5 meter length of the line charge is 40 nanocoulomb, right? And the unit of charge q and the unit of flux lines, it is coulombs only. Both are one and the same. So psi equal to q, that is equal to 40 nanocoulomb. Okay, I hope you understood this. Then next, just locate line charge at y equal to 0 and z equal to 0. You can try to locate. Just I will give 5 seconds or 10 seconds time. Try to locate it. I will draw it later. You try to locate it, then cross verify yourself. Just I will give 5 to 10 seconds time. I will wait. Locate the line charge at y equal to 0 and z equal to 0. Try to locate it. Location of points, location of lines we have seen. Okay, I hope you have done it. Just verify it. So x, y, z. So y is 0, z is 0. Y is 0, z is 0 means I can locate it here. It is coming out of the board and going into the board, but this looks as a point and not as a line charge, right? So I will redraw it once again. So here, so y is 0 and z is 0 means it should be parallel to x axis, right? So the line charge, yes, it is located like this on x axis, entire x axis. Sorry, don't draw multiple lines. What I am doing here, right? This is the line charge, royal, right? This is, we have located the line charge y equal to 0 and z equal to 0. On this line charge, you locate any point, y is 0 and z is 0, right? I hope it is clear to you people, right? Yes. Yep. Next, we'll take up this numerical. This is conceptual based. I have told conceptual means no need to solve it. It is based on the concept, what we have learnt, right? The electric flux density, the flux, psi, all those things will make use of those concepts what we have learned previously. Okay, just I'll read out the problem. Given a 60 microcoulomb point charge located at the origin, right? It is at the origin. Find the total electric flux passing through first part, that portion of the sphere r equal to 26 centimeter bounded by theta. It is 0 to pi by 2 and phi 0 to pi by 2. So we'll take a part A, part B later and part C later. Part A. So let me take up this. R is 26 centimeter, radius is 26 centimeter. Theta is 0 to 90 degree. 0 to 90 degree. And phi is also 0 to 90 degree. Then it is not a complete sphere. If theta is 0 to 180, 0 to pi, and phi is 0 to 360 degree, 2 pi, then complete sphere is formed. But just portion of a sphere is formed. These are the bounds. R is 26 centimeter, theta is 0 to 90 degree, and phi is 0 to 90 degree. Means 1/8 of a sphere. It is not a complete sphere. So means 1/8 of a sphere. Just I will draw it like this. Observe here. I will get like this. Part A. Okay, 1/8 of a sphere is formed. Because radius r is 26 centimeter, theta is, see here, 0 to 90 degree from here to here. This is x axis, y axis, z axis. 0 to 90 means it is projected onto xy plane. 0 to 180 it should come if it is a sphere, right? But 0 to 90 degree. Then phi is 0 to 90 degree. From x axis we measure the angle phi. It is 0 to 90 degree here, right? So 1/8 of a sphere. So charge is located here at the origin. That is Q. That is how much? 60 microcoulomb. Right? So what they have asked, find out the total electric flux psi. What is psi? They have asked. But this charge Q is at the origin, right, at the center. So suppose the charge Q is enclosed in this complete sphere. Let me take this is as a, it is not a circle, actually it's a sphere. If it is enclosed in this Gaussian surface, the imaginary surface, then the psi is the Q only, that is 60 microcoulomb. Q is 60 microcoulomb. But here it is not the complete sphere, it is 1/8 of a sphere. So psi is equal to, here in this case, q by 8 because 1/8 divided by 8 because in all the directions the flux lines leaving this 1/8 of a sphere only some amount of flux lines are living here, right? We will not consider the other surface, we will consider only this surface, right? So q by 8, 60 microcoulomb divided by 8. So do it, how much you will get? 60 divided by 8, 7.5, 7.5 microcoulombs. I hope you got this. If any doubts, you can ask. If it is a complete sphere, then what is the total charge enclosed or the number of flux lines leaving the surface means it is 60 microcoulomb. But in the part A, what they have asked, they given r is 26 centimeter, theta is 0 to 90 degree, phi is 0 to 90 degree. Then what is the amount of flux lines leaving this surface? 1/8 of a sphere. So divide it by 8, right? Because it is symmetry is there. Everywhere the field lines are symmetrical in nature. 1/8 of a sphere, right? 7.5 microcoulombs. If it is entire sphere, 7.5 into 8, 60 microcoulombs I will get. Is it fine? So this is the answer. Next we will take up the part B. Part B. The same thing, given 60 microcoulomb point charge located at the origin, find the total electric flux passing through. This part B I am taking. The closed surface defined by rho equal to 26 centimeter and z equal to plus or minus 26 centimeter. Means some cylindrical surface is formed. Here the spherical surface is formed with these bounds. Here the cylindrical surface we will see. We will try to draw it. What we will get? Rho is radius of the cylinder is 26 centimeter and z height is plus 26 and minus 26 centimeter. So I will draw it, try to draw it. X, Y and Z. Okay, the surface formed is cylindrical, I know it. So I will draw the cylinder. I will draw it, then I will explain to you people. Observe here, radius rho is how much? 26 centimeter, yes. Then Z is plus 26. Here Z is plus 26 centimeter and here Z in the negative Z axis extended. Here it is minus 26. So Z equal to plus 26 and minus, it is varying, height is varying from minus 26 centimeter to plus 26 centimeter along Z axis. And phi, they have not given phi, but it is understood that phi is varying from 0 to 360 degree, 0 to 2 pi. It is understood. Rho is lying between 0 to 26 centimeter and phi is 0 to 2 pi and Z is lying between minus 26 centimeter to plus 26 centimeter. So these are the bounds that is given, but phi is not given. So closed surface means phi has to be 0 to 360 degree, 2 pi radians, right? Okay, then where the charge is located? Here, plus q, and it is equal to 60 microcoulomb. So what is the flux line that is crossing this surface? So this is, let me treat this as Gaussian surface, imaginary surface. The total amount of charge enclosed by the surface is 60 microcoulomb only. So psi is equal to q and that is equal to 60 microcoulomb, right? This is concept based. Don't try to apply any formula here. The concept is there. What is the total amount of charge enclosed in this surface? It is q, right? The flux lines everywhere, they leave the surface. So psi equal to q, that is equal to 60 microcoulomb. Then coming to the part C, the plane z equal to 26 centimeter. Yes, we will try to draw z equal to 26 centimeter plane. X axis, Y axis and Z axis. And at the origin, plus Q, that is 60 microcoulomb is located here. Then Z equal to 26 centimeter means parallel to X and Y axis, the plane should be right. So parallel to Y axis, then parallel to X axis. This is the plane, but it is infinite plane. What I have drawn is finite. So just above this charge, this Z equal to 26 centimeter, right? This is the plane, Z equal to 26 centimeter. So it is covering, this plane is extending from minus infinity to plus infinity along Y axis, and along X axis minus infinity to plus infinity, means, right, it is varying from minus infinity to plus infinity along X axis, then along Y axis minus infinity to plus infinity along Y axis, means infinite sheet, Z equal to 26 centimeter, right? It is covering that entire thing, right? So I want to find out what is the total amount of flux lines leaving this surface. Psi, what is psi? I want to find out. Observe here, point charge means the pattern right? We know, we draw the nature of field like this, right? We draw the nature of field like this practically. Alright, so z equal to 26 centimeter plane is here, z equal to 26 centimeter plane is here, right? So if another z equal to 26 means 50%, right? These all flux lines will cross this surface, these all flux lines. So another 50% will cross the below surface, right? But we have asked to find out how many number of flux lines will cross this, right? Psi equal to q. So psi equal to q, q is nothing but here the q divided by 2, because 50% of the lines will cross z equal to 26 centimeter, another 50% another plane lying below this, another plane, but they have not asked this, right? So q by 2, q is 60 microcoulomb divided by 2, 60 by 2 is 30 microcoulomb, right? Getting answer is very easy, but we have to explain all these things, concepts, then only we should arrive at, we will arrive at the answer, not just, right? I hope you have understood this. If any doubts are there, please stop me at that moment and you can ask, right? I hope you understood this conceptual based problem, right? Okay, next we'll try to move to the next problem. This is the last problem of today's class. Next we'll see. Okay, calculate the electric flux density D in the rectangular coordinates. Here they have asked in rectangular coordinates means it should be in terms of ax, ay, az only, right? Not in other coordinates, right? Rectangular coordinates at point P of 2, minus 3, 6. Yes, it is better to give whether I want my answer to be in rectangular coordinates or cylindrical or spherical, right? But he is very clear here. Calculate the vector D in rectangular coordinates at point P of 2, minus 3, 6 produced by part A. There are three parts here, part A, part B, part C. Three different problems are there. I will take up only part A first. A point charge QA equal to 55 millicoulomb at this point, right? So D due to point charge. So part A. So point charge is given, QA is equal to 55 millicoulomb at, he has given Q, but QA is there, I will call it as A. I will not call it as Q. I will change this. A of minus 2, comma 3, comma minus 2, comma 3, comma minus 6. Right? Then field point. So point charge is here plus QA. Right? Then another point P is here 2, minus 3, 6. And here A of minus 2, comma 3, comma minus 6. This is the source point, but I will not call this as field point, but here the field point is lying here, but what is electric flux density at this point P is asking. So we know D due to point charge, Q by 4 pi R square, the distance between this to this, right? So I will join source point to field point, I will call it as RAP, and unit vector is AAP. Q by 4 pi R square into AR. R square is nothing but RAP square here into AR. AR is AAP, right? So he has told in rectangular coordinates, RAP, AAP means XYZ will come into picture. If I make use of, I can look at the same charge in spherical and the answer will be different. It will be in radial direction, right? Okay, we'll see, we'll try to calculate RAP. So A to P. So 2 minus of minus 2 plus 2, 4AX. Then minus 3, minus 3, minus 6 AY. 6 minus of minus 6 plus 6, 12 AZ. So calculate the magnitude RAP. It is equal to under root of 4 square is 16, 4 4 is 16, 6 square is 6 is the third 6, plus 12 square, 12 square. So we got it as 14, RAP is 14 after calculating. So substitute here, D vector is equal to Q is nothing but 55 milli, 55 into 10 power minus 3 is milli, divided by 4 into pi. Don't write epsilon naught, because epsilon naught will not come into picture whenever we are calculating electric flux density. It comes into picture only in electric field intensity. E is equal to Q by 4 pi epsilon naught R square into AR. So don't write epsilon naught here. RAP square 14 square into AAP is RAP 4AX minus 6 AY plus 12 AZ divided by RAP. RAP I will make it cube. I will take here. This RAP I am taking it here. So I will calculate here how much I will get. So 55 exponential minus 3 divided by 4 into pi into 14 cube. 14 cube. So I am getting it as 1.595. So I will write it 1.595 into 10 power minus 6 into 4ax minus 6ay plus 12az. Will multiply. So d vector is equal to 1.595 exponential minus 6 into 4. So 6.38 into 10 power minus 6. 6.38 into 10 power minus 6ax. Then minus 1.595 into 6. So 9.57 minus 9.57 into 10 power minus 6 ay. Then multiply this with 12 plus into 12. So 1 point, okay, I want the in terms of, okay. So I'm getting it as 19.14 into 10 power minus 6 az. So take 10 power minus 6 and write it common. So we are getting the same answer here, right? 6.38 ax 9 minus 9.57 ay 19.4 micro. We will take 10 power minus 6 outside, right? 6.38 ax minus 9.57 ay plus 19.14 az. Yes, put bracket and write down 10 power minus 6 is nothing but micro coulomb per meter square. Right? I hope you got this. Next, we'll solve part B. Part B. Part C, I will leave it to you people just by giving the hint. Part B, I'll solve it. Part B. A uniform line charge rho L equal to 20 millicoulomb per meter on the x-axis. Rho L equal to 20 millicoulomb per meter. Rho L equal to 20 millicoulomb per meter on x-axis. On x-axis. Right? So on x-axis the line charge is there. X, Y, Z. So on x-axis means entire x-axis. This is the rho L 20 millicoulomb per meter on x-axis, and point P is located at this one 2 minus 3 6 somewhere. 2 minus 3 6 somewhere here. Right, point P is located here. Then we know D due to the line charge formula, right? So we have written here, right? Due to line charge is rho L by 2 pi rho, but we know it is rho L by 2 pi epsilon rho into a rho for this electric field details. Rho L by 2 pi rho into a rho. Rho L by 2 pi rho into a rho. So we'll draw the perpendicular distance, right? So on x-axis means y is 0, z is 0. What about x? So point P, what are the coordinates of point P? We will write. So 2 minus 3 6. 2 minus 3 6, right? So observe x. If it has to be perpendicular means it has to be 2. 2 comma 0, right? I will take the same point, right? 2 here. X coordinate is 2 here. I will take 2 here, right? So this rho is nothing but the distance from, let me call this as A. So I will rewrite the formula rho L by 2 pi A to P, RAP, A to P, RAP vector, and unit vector is A to P. Just I am rewriting as per my convenience. So RAP into AAP. So find out RAP here. First vector RAP. So A to P. So source point to field point. This is field point, right? So R A to P means 2 minus 2x will get cancelled. So minus 3 AY, Y component, 6 minus 0, Z component 6AZ, and RAP, the magnitude RAP is equal to how much? So root of 3 square is 9 plus 6 square is 36. So it is 6.708. 6.708. So substitute here, D vector is equal to rho L is how much? 20 milli. Milli means 10 power minus 3 millicoulomb per meter divided by 2 into pi into RAP is how much? 6.708 into AAP. AAP is RAP minus 3AY divided by 6AZ divided by RAP. RAP means I will make it square, this one. RAP will come here, but RAP I will take it here. So calculate this, how much you will get? So 20 exponential minus 3 divided by 2 into pi into 6.708 square. So I am getting it as 70.739 into 10 power minus 6 into minus 3AY plus 6AZ. So I will take this 10 power minus 6 outside, just I will multiply 70.739 with this. So 70.739 into minus 3. So minus 212.217 AY. Then plus multiply that 70.739 into 6. So I am getting it as 424.434 AZ. Put it in bracket. 10 power minus 6 means micro, right? Micro coulomb per meter square. Just verify, minus 212 plus 424. Minus 212 AY 424, right? Micro coulomb per meter square. So part D I am leaving it to you people, right? So part D, just I will give the hint here for part C. Rho S is given 120 microcoulomb per meter square and it is on the plane Z equal to minus 5 meter. Draw the diagram. Then Then formula you have to use, D is equal to, we know E due to surface charge is rho S by 2 epsilon naught, but epsilon naught will not come into picture, into the unit normal vector AN, right? So what is this AN, you have to find out. So calculate this. So it is in AZ, AN is AZ, it is coming here by looking at the answer, but don't do it, just calculate and finally you have to get the answer as 60 AZ microcoulomb per meter square. I hope you will do this, right? So we will wind up the class here. I'll stop recording.